Okay, all right. So let us begin today's session. This is live session number 7. And in the last session, we have discussed about the load flow analysis of in distribution networks. And in that session, we have seen the one of the most common approach, that is backward forward load sweep, load flow sweep approach, that we have seen in the last session, and we have solved problems based on the backward forward load flow analysis. Now in today's session, we are going to see the problems based on the reactive power compensation with the capacitor banks in the distribution networks. So let us see here the shunt capacitor for the power factor correction, and here we see the power triangle. So here we have substation and the load is connected at one of the node, and by adding the capacitors, the reactive power component Q, that is of the apparent power S of the load, can be reduced or totally suppressed. Here we have assumed a load that is supplied with a real power P1, lagging reactive power Q1, and the apparent power S1 at a lagging power factor of cos theta 1. So we can make the power triangle. So this is P1, and in quadrature with P1, Q1, and and this whole will make this apparent power S1, and this is the theta 1. If we take the cosine of theta 1, that will give you power factor. So power factor is cos theta 1 is equal to P1 divided by S1, and you can you can make this trigonometry expression. Now, in order to do reactive power compensation with the capacitor bank, a shunt capacitor is connected at the load end of capacity QC, and therefore this improves the power factor, and this improvement of power factor from cos theta 1 to cos theta 2. Let us assume this after reactive power compensation, that is theta 2. So uh, how this power triangle will become? So we can see here that from the distribution substation, now the reactive power demand from the substation is that it has reduced, that is Q2, and that becomes Q1 minus QC. So before reactive power compensation it is Q1, and after doing reactive power compensation, this reactive power demand from the substation reduces, and that becomes Q2. Therefore power factor will improve, and this is the power factor, that is the ratio P1 divided by S2, and this is the trigonometric expression for this improved power factor. So these are very basic things. Just you can recap. And one of the example for power factor correction is that, let us assume we have a 100 kVA load with a power factor of 0.8 lagging, and you would like to correct this power factor to 0.95 lagging. What would be the capacitor size? So this power factor is given as 0.8. So we can find the power factor angle, that will be coming as 36.9 degree. And from this given data, apparent power is 100 kVA and power factor is 0.8. From there you can find the active power. So it is equal to 80 kilowatt, and Q will become 60 kVAr, since cos phi is 0.8. So sin phi is 0.6. So you will get reactive power as 60 kVAr. Now in order to in order to improve the power factor improved from 0.8 lagging to 0.95 lagging. So what should be the capacitor size? So let us, this power factor desired is 0.95. Therefore, this angle, power factor angle will become 18.2 degree. So if you just need to this trigonometry expression, use this trigonometry expression tan 18.2 degree, that is 60 minus QC divided by 80. So you will get the capacity of the capacitor bank, and that will come at 33.7 kVAr. So in nutshell, this power factor triangle is very important. If you are able to make this power factor, if you are able to make this power triangle yeah, by understanding the question, you can solve the problem very easily. And this is from the class notes. Like what is the effect of active power on power factor? Here, just we have considered the active power demand for the load is fixed, and if you assume this load is of inductive nature, then reactive power demand and this VA demand of the load increases with reduction of power factor. And in another case, here we have assumed the apparent power demand for the load is fixed, and this if this reactive power get worsen, then the load is consuming lower active power with reduction of power factor, and also this reactive power demand will increase with the reduction of power factor. Now these are very important. The concept of leading and lagging power factors. So the concept of lagging leading power factor depends on the direction of flow of reactive power. And we have for load, if the power factor is lagging, that means that denotes that it is of inductive in nature. And power factor is lagging means that Q is positive, and that means that load consumes reactive power. If nothing is given about the reactive power, that you have to suppose that this is for lagging reactive power. So in another way, you can also write load consumes lagging reactive power, and just reversing all these things consumes in the just a positive consumption is supply, or consumption is supply. So if you are writing in that way, load supplies leading reactive power. So these are both are same things. If load consumes lagging reactive power, that means load supplies leading reactive power. And now for if the power factor is leading, that means Q is negative. That means that that denotes the load is of capacitive nature, and that means that load supplies reactive power, and simply reactive power is written. That means that load supplies lagging reactive power. And now just reversing the term supply with consumption, just you have to also reverse this lagging to leading. So that means load consumes leading reactive power. If you have any doubt till here, you can ask. Otherwise, we can move forward. Now, the basic nature, a fundamental nature of load is that it consumes. So sign convention for load is positive. That means it consumes real reactive power. And for the fundamental nature of generator, or the basic nature for generator, is that it supplies. It supplies something. It delivers. It supplies or it delivers. So that the sign convention is positive for generator if supplies real or reactive power. Now for generator, if Q is greater than 0, so that it supplies reactive power, and simply supply reactive power means that it means that supplies lagging reactive power, and also it consumes leading reactive power. And for generator, if Q is negative, it means that it consumes reactive power. It co- it also means that it consumes lagging reactive power, and just reversing the terms, consumption with supply or deliver, and therefore we have to also reverse this lagging with leading, so it supplies leading reactive power. And and for load you have to just reverse the things. And for load, if Q is positive, it means that it consumes reactive power because it matches with the fundamental property of load, basic nature of load, that it consumes something, and for generator it supplies or it delivers something. So if reactive power is positive, that means it consumes reactive power, so it consumes lagging reactive power, and now reversing the things, it supplies leading reactive power. Now the last point is that if Q is negative for load, it means that it supplies reactive power, and it also says that it supplies lagging reactive power, and just reversing the terms you will get it consumes leading reactive power. Till here any doubt? If there is no doubt, we can move further.
Sir, good evening, sir.
Yes, good evening.
Yeah, sorry, I have joined late. Uh, Basically,
Okay,
you mentioned sign convention is positive for generator. It supplies real or reactive power. Uh,
yeah,
so basically, when we solve the problems, if power across any device is positive, it means it consumes, or yeah, if negative, it means it delivers. In network theorems, yeah, network circuits. But here, assumption is some different.
no, no, it is not different. You have to clarify that what type of reactive power it is. Like for capacitor, Q is coming as negative, right? So Q is coming negative, so that means it supplies lagging reactive power. And for like if you have in inductor, that means Q is positive, so it consumes lagging reactive power. Can you? I'm not getting miss clearly what you are saying.
Actually, sir, in first two statement, you have mentioned sign convention is positive for load if consumes real reactive power,
Yeah,
and second statement, sign convention is positive for generators if supplies real reactive power.
yeah. For that means the synchronous generator here, I'm you can take it as example. So if for generator, if Q is positive, it means that it supplies lagging reactive power. But for load, it does not mean that it supplies lagging reactive power because because it is consuming. So it just reverses for the generator and for the load case. Here I have written the here I have written in that way, like this is the basic for nature of load and generator. So in that way the sign convention is has been assumed. Like for load, the basic nature that it should consume. So that's why if it is positive, that means it consumes real reactive power, and for generator, that means it supplies or it delivers. So you have to take the positive sign if it supplies a real or reactive power. And if in simple in other way, simply in any problem or anywhere it is written reactive power, that means you have to assume that it means lagging reactive power, not the leading reactive power. So many way, in almost every place you will see that simply it is written reactive power, but they not mention about that it is of lagging nature or leading nature. So there you have to assume that it is lagging reactive power.
Okay, sir. But actually, when we solve the networks problem, so if power is positive across any element, so we assume that it consumes the power. If power is negative across any element, it means it delivers the power in case of network circuit.
Yeah, you are saying that P is positive, that means consume active or reactive. So in network, we are dealing with the loads. That's why. So this first point is very important. Second one is we are not usually use like for generator case. You are telling right because wherever you are doing the things where you are solving the problems that is related with the load, not with the generator. Okay.
Yeah, okay, sir. Thank you.
Yeah. Yeah, this is the most common because we are dealing with load, so we don't take care of the generator. For the but this should be clarify. For generator, it is different. But if it is load, then it is very means like if P is positive, then it consumes, or if P is negative, then it means delivers. So you are telling correct. Now, now for this capacitor size and allocation of capacitor banks in the distribution networks, we have two expressions. First one is the lambda, and lambda is the ratio of reactive current at the end of line segment to the reactive current at the beginning of line segment. And for uniformly distributed load, this I2 will become 0, and therefore we will get lambda is equal to 0. And for lumped load or concentrated load, this I2 will be equal to I1 because all the loads we have assumed that concentrated at the end of line segment. Therefore, I2 equal to I1 and this lambda equal to 1. And another one expression is that alpha, and alpha is the reciprocal of 1 plus lambda square. Now the another term, that is C, that is degree of capacitive compensation. So it is the ratio of kVA of capacitor installed to the total reactive load. So these two terms are used for the used for the capacitor bank placement in the for the analytical method. Now for this power loss reduction expression is that 3 alpha divided by 1 by minus lambda into C minus C square plus CQ divided 4. These expression that are not that much important. You have to uh, just know the things like if you differentiate with respect to C and by equating to 0, we get the optimal value of C, that is capacitor size to two-third of the total reactive power demand. And this placing of capacitor bank equal to two-third of 1 divided by 1 minus lambda. And therefore this power loss reduction expression will become 8 divided by 9 into alpha 1 minus lambda. And if we are having uniformly distributed load, that is lambda is equal to 0, this power loss reduction will become 8 divided by 9 per unit, that is coming as 89%. For the capacitor placed at x is equal to two-third of per unit distance with c is equal to two-third per unit size. So this is well known two-third thumb rule for capacitor placement. So this is very important. So for uniformly distributed load, the power loss reduction will be 8 divided by 9 per unit for the capacitor placed at x is equal to 2 two-third of per unit distance with capacitor size of two-third of the total reactive power demand. So now coming to the problem. So the first problem is that, and this is common data for question 1 to question 5. And the first problem is that let us see this first see the data. A balanced star connected three-phase load draws 1500 kilowatt power at zero point 0.8 power factor. The load in voltage is 11 kV at 50 Hz. A three-phase capacitor bank is used for compensation so that power factor is improved. And here it is asking that what is the line current drawn by the load before compensation. So all of you start solve problem. Whoever is getting answer can type your answer in the chat box. So what is the line current drawn by the load before the compensation? Here the active power is given, that is 1500 kilowatt, and power factor is given as 0.8 before the compensation, and load in voltage is given 11 kV, that is line to line voltage at 50 Hertz. So from this data we can find the line current. Root 3 of VL IL cos phi. VL is 11 kV into IL cos phi 0.8. So you will get IL as 98.41 ampere. So B is the correct answer. Yes, just one thing you are correct. Another one, please start solve the problem. So just record this data. IL is equal to 98.41 ampere. We will use this data for the next problem. Now it is saying that if the power factor is improved from 0.8 to infinity using a delta connected capacitor bank, the reactive power supplied by each capacitor and the capacitance of each capacitor are respectively. So we have to find the reactive power. So reactive power, we know the expression, that is root 3 VL IL sin phi. VL is 11 kV, and we have found the line current 98.41 ampere. Sin phi cos phi 0.8. So sin phi will become 0.6. So into 0.6. So you will get reactive power as 1124.97 kVAR. So that is approximately equal to 1125 kVAR. So that we got the reactive power supplied by the capacitor bank, and now the capacitance of each capacitor we have to find. So if we see, since this is a delta connected capacitor bank, so we will use the line voltage. Like suppose this is line, and here these capacitors are delta connected. So like this. So here we can see that across each capacitor line voltage is appearing. So we can write Q equal to 3 into VL square XC. So this is total reactive power. I think to write here. So each capacitor is supplying VL square divided by XC reactive power. So it will multiplied with 3 to get the total reactive power supplied by this delta connected capacitor bank. So 1125 kVAR into 3 VL square. VL square is 11 kV and XC is 1 divided by 2 pi FC. Therefore 100 pi into C. So on simplification of this, you will get 9.865 into 10 to the power minus 6, 10 to the power minus 6 farad. So it is equal to 9.865 microfarad. So one correction is there, all values are in microfarad, not in millifarad. So this is the total reactive power supplied by the capacitor bank. And in this problem, we have to answer this reactive power supplied by each capacitor. So it should be divided by 3. Reactive power supplied by each capacitor equal to 1125 divided by 3 kVAR. So it become 375 kVAR. So therefore B is the correct answer. 375 kVAR and 9.865 microfarad. So how we got A answer? 1125 Priyadarshini Rahul.
We have not divided by 3.
Okay, correct, correct. So yeah, here it is asking that reactive power supplied by each capacitor, not by the capacitor bank. Now let us move to the next problem. What is the line current drawn by the load after compensation? So here it is given that load draws 1500 kilowatt power, and it is telling that this it is telling that in the previous question this power factor is improved to unity power factor. Therefore this A is equal to P, because after compensation there is no reactive power demand from the generator side. After compensation, this P equal to S is not good way to write. So after compensation, A is equal to root 3 in VLIL. Since active power is 1500 kilowatt at 0.8 power factor. So after unity power factor, this will become same to apparent power, and cos phi is 1. So there is no, in either way you can write. So cos phi is 1. So you will write here P equal to 1500 kilowatt into root 3 times VL. VL is 11 kV into IL. Cos phi is unity power factor, so it is 1.0. From here you will get IL 78.73 ampere. Therefore, C is the correct answer. Yes, Jaswant, Rahul, both of you are correct. Now let us move to the next problem. Now it is telling that if the power factor is improved from 0.8 to 0.9 using a star connected capacitor bank, the reactive power supplied by each capacitor is. So here again be cautious. It is not reactive power supplied by the capacitor bank. It is supplied by the each capacitor. So we can make the power triangle, or in either way, if you know directly the expression for reactive power in terms of tan theta, in that way you can also solve. But the fundamental way we are going to solve that approach, that is with the help of power triangle. So active power is given as 1500 kilowatt. It remains the same. Now this reactive power demand before the compensation, that we denote as QL. So it is 1125 kVAR. Now we are doing the reactive power compensation. So this reactive power demand will get reduced. So it will become QL dash. QL dash we will find. So this is the power triangle before the compensation, and this is the power triangle after the compensation. So QL we have already found, that is 1125 kVAR previously, and PL that we given in the problem 1500 kilowatt. So this is the before compensation power factor triangle before the compensation, and suppose this is the power factor angle after the compensation. So tan phi you can write, QL dash divided by 1500 kilowatt, and this phi is cos inverse 0.9 QL dash upon 1500 kilowatt. So we will get the answer in kVAR. So QL dash will become 0.48 into 1500, so it will give you 726.48 kVAR. And QL dash is QL minus QC, so QL dash is QL minus QC. So from here we will get QC, so QC will come as 398.5168 kVAR. So again, this is the total reactive power supplied by the capacitor bank, and here we have to find this supplied by each capacitor. So the reactive power supplied by each capacitor will become 1/3 of the total capacitor reactive power demand. Total reactive power supplied by the capacitor by each capacitor divided by 3. So it will come as 132.83 kVAR. So D is the correct answer. If you face any doubt, anything, you can ask, you can interrupt me. So all of you are correct. Jaswant, Dharmender, Rahul, Sujata, Lekha, all of you are doing very nice. Now moving to the next problem. The capacitance of each capacitor corresponding to question 4. So now we have found this reactive power. Reactive power we have found that is being supplied by each capacitor is 132.83 kVAR. So this data I have provided you. Now we have to find the capacitance of each capacitor. So for a star connected, since the capacitor bank are in a star connection, so you can make one another line that is connected with the neutral. So across each capacitor we can see the phase voltage appear. So we have to do the simplification for the phase voltage. So QC you can write V phase square upon XC, and XC is 100 pi C, 1 divided by 100 pi C. So you can write 132.83 into 10 to the power 3 kVAR. So line voltage is 11 kV, so it will phase voltage be 11 divided by root 3 kVAR, root 3 kV into 10 to the power 6 divided by 1 upon 100 pi C. Now putting all these values, you will get 10.48 microfarad. So again, there is mistake. All the options are in microfarad. Therefore, D is the correct answer. Yes, Sujata, Rahul, Dharmender, all of you are correct. I think this you replied for previous problem. So let's see for the next problem. Till here any doubt you can ask. Otherwise we can move further. So we have to just take care what is the capacitor bank, how is the configuration of capacitor bank. If it is delta connected, then take the line to line voltage, and if it is the star connected, then take the phase voltage. Based on your how you analyze the network, based on that you can find. There are many other ways you can also find, but the more simplified way, I think this is the one. For delta connected load, we just take the line to line voltage, and for a star connected capacitor bank, you take the phase voltage. Now the next problem. This is the multiple select question. Which of the following consume leading reactive power? So there are more than one options are correct. Multiple select question. Anyone knows the answer, they can reply. Visual flowing consume leading reactive power. First option is transformer. Second option is overexcited synchronous generator. C option is transmission line with loading greater than surge impedance loading. D option is capacitor. B and D. Yeah, Jaswant, Rahul, Dharmender, Sujata, Lekha, all of you are correct. Very good. So this transformer is acting as, like, if you take the equivalent diagram for transformer, then you can represent like a, with the help of leakage inductance. So moreover it behaves like a inductor. So it consumes lagging reactive power. So this will be not the correct answer. An overexcited synchronous generator or overexcited synchronous motor, both are both supplies lagging reactive power. That means it consumes leading reactive power. So this is correct. Now this transmission line with loading greater than surge impedance loading. So I have written some points regarding surge impedance loading. Like you are familiar in the power system. Surge impedance loading, that is defined as the power load in which the total reactive power of the line becomes zero. And this reactive power generated by the shunt capacitance that is being consumed by the series inductance of the line. And if load is greater than surge impedance loading, that means receiving in voltage is less than sending in voltage. This means that you have to add the shunt capacitor so that you can restore the voltage. And if load is less than surge impedance loading, that means receiving in voltage greater than sending in voltage. It means that shunt inductors are added to restore the voltage. So here the case is this one. transmission line with loading greater than surge impedance loading. So you have to do the you have to add the shunt capacitor at the load end to restore the voltage. And also here in this problem they are asking about the which of the consume leading reactive power. So this will be the case. So transmission line with loading greater than surge impedance loading, that means receiving voltage will become less than sending voltage, and it requires compensation with the shunt capacitor. So it means that it will not consume leading reactive power. So this is also incorrect. And the last is correct is capacitor consumes leading reactive power. That means it supplies the lagging reactive power. So this is true. So B and D are correct. Any doubt here till here? Okay, we can solve one more problem. So now moving to the next problem. In this problem, visual flowing compensator can be used to compensate Ferranti effect and leading load power factor respectively. So this is single choice question. Only one answer is correct. So what do you think? Which of the flowing compensator can be used to compensate Ferranti effect and leading load power factor? In Ferranti effect, this happens in the case of light load condition in medium or long transmission line due to capacitance effect. This I think you are also familiar with the Ferranti effect. Rahul, but I got one answer. Dharmender Rahul, C. Yes, it is correct. C is correct. So for both the Ferranti effect and leading load power factor, we use the shunt inductors. And if we look into the Ferranti effect that occurs in the light load condition for or no load condition for a medium and long transmission line due to capacitance effect of the transmission line. So therefore, we require shunt reactor that will reduce the effect of capacitance, and in that way the Ferranti effect will get reduced. And for leading load power factor, it obvious that shunt inductor we have to use for the compensation. So I am sending you one link so that you can join, and we will continue in that session. Sorry for this inconvenience. Lekha, please join the new session. Lekha, if you are here, then please join the new session. I am closing this previous session. So we are here. Now we can continue from here. So let us see the next problem. Assume a balanced three-phase 400 volt cable circuit is rated at 120 ampere but carrying a load current of 160 ampere at zero point 0.6 power factor. Determine the rating of capacitor bank needed to reduce the current to 120 ampere. So here it is given that the cable is loaded more than its rated capacity. So you have to do the compensation with the help of capacitor bank, and you have to reduce the current to its rated capacity of 120 ampere. In that case, you have to determine the rating of capacitor bank. So first we will find the uh, active and reactive power demand, since cos phi is given as 0.65. Therefore, we can find the active power demand root 3 VL IL cos phi PL. You will get, so 400 volt is the line to line voltage, IL is 160 ampere, and cos phi is 0.65. So you will get 72.053 kilowatt. Now, since this, if you take the find the power factor angle for this 0.65 power factor, then you will get 49.46 degree. So this will give you 49.46 degree. So therefore, QL you can also get root 3 VL IL sin phi. So QL will root 3 times 400, IL is 160 sin phi. So from here you will also get sin phi. Sin phi will become 0.76. Sin phi will become 0.76. So it is 84.24 kVAR. Now this active power will remain same as it is for this new current also. So from there we can find the uh, power factor from that way also. Now after doing the compensation, you can tell that you can write that PL will remain same as it is. So it is 72.053 kilowatt into root 3 VL. VL is 400. IL will become 120. So therefore we can find the new power factor angle. So you can new power factor that you can represent as cos phi 1. So we will get cos phi 1 as 0.867, and from there you will get phi 1 as 29.93 degree. So sin phi 1 is 0.4988. So therefore new QL dash will be, that is that is from the that is flowing through the cable, reactive power flowing through the cable, that will be root 3 times 400 into 120. Sin phi 1 will be 0.4988. So it will become 441.476 kVAR. Therefore you can write the rating of capacitor bank to reduce the current to 120 ampere. That will be QL minus QL dash, because the extra reactive power that is being supplied by this capacitor bank. So before conversion it is 84.24 kVAR, and after conversion it is 41.46 kVAR. So this will become 42.763 kVAR. So correct answer is A. Any doubt in this problem? Yes, Jaswant, Sujata, both of you are correct. Dharmender, you are also correct. So A is the correct answer. Now moving to the next problem. Assume that a 1.2 kV single phase circuit feeds a load of 120 kilowatt measured by a wattmeter at a lagging load factor, and the load current is 200 ampere. If it is desired to improve the power factor, then what will be the new corrected power factor after installing a shunt capacitor unit with a rating of 120 kVAR? So be careful, this is a single phase circuit. So for single phase circuit, we can write the power equation. This is single phase circuit. So first we will find the previous power factor and the active reactive power. Since this active power is given, load active power is 120 kilowatt, 180 kilowatt. So for single phase, that will be VI cos phi 180 kilowatt. Voltage is 1.2 kV, and the load current is also given, that is 200 ampere. From here we can find the power factor. So power factor will come as 0.75. Therefore power factor angle will be 41.41 degree. From there, from here we can find the reactive power of the load. So Vi sin phi 1.2 kV into 200 ampere sin 41.41 degree will be 0.66. So it will give you 158.745 kVAr. So this is the reactive power of the load. Now here it is telling that we have to what will the new corrected power factor after installing a shunt capacitor unit of rating 120 kVAr. So they have provided this QC value 120 kVAr. So QL dash will become will become QL minus QC 158.745 minus 120 kVAr. So it will become 38.745 kVAr. Therefore, cos phi new power factor will be, let us take cos phi 1. So it will be PL upon this hypotenuse will be apparent power. So it is PL square plus QL dash square, or simple way you can, this way you can also find, otherwise you can use the tan phi. So cos phi 1 PL is 180 kilowatt under root of 180 square, QL dash is 38.745 kVAr square. So it is 180 divided by 184.123. So this will give you 0.9776. It is approximately coming as 0.978. So D is the correct answer. Yes, Jaswant, Sujata, Lekha, all of you are correct. Now moving to the next problem. Question number 10. For a feeder with uniformly distributed load, a fixed capacitor bank rated at two-thirds of the total reactive load and located at two-thirds of the distance out on the feeder from the source gives loss reduction. So it is uniformly distributed load. So first data they have provided you that uniformly distributed load. Uniformly distributed load means I2 will become 0. This reactive component of current at the last point of the feeder will be 0, and we know that lambda is equal to I2 upon I1, so it will also become 0. And from here you can also say that alpha, that is reciprocal of 1 plus lambda square. Since lambda equal to 0, therefore alpha become also 1. And this capacitor bank capacity is given, it is given as the two-third of the total reactive load, and location of capacitor bank is also given x1, that is given as two-third of the distance out on the feeder. So you have to find the loss reduction. You can directly use the last slide of the this reactive power conversion with the help of capacitor banks. There we have found this power loss reduction as 8 divided by 9 into alpha upon 1 minus lambda. From there you will get directly 89%. Other way, for single capacitor bank, we know the expression for single capacitor bank. We know that per unit power loss reduction is 3cx1 upon 1 plus lambda square into 2 minus x1 plus lambda x1 minus c. So here you have to put all this value. So this is given in the per unit form. So you have to, here the answers are given in percentage. So you have to multiply with 100. So we know that 1 divided by lambda plus lambda square is alpha. So from there 3 alpha is 1. So alpha is 1. C value is given as 2/3 and x1 value is given as 2/3. 2 minus 2 upon 3 plus lambda x1 lambda is 0 minus c is 2/3 2 upon 3 into 100%. So this will give you 4 upon 3 into 4 upon 3 minus 2 upon 3 into 100%. So it will give you 4 into 2 8 upon 9 into 100. So it is giving you 88.889, that is coming as 89%. Therefore A is the correct answer. Yes, A is the correct answer. Dharmender, you are correct. Sujata. Now moving forward for the next problem. It is common data for 11 to 15. A three-phase distribution feeder is drawing 120 ampere to supply a lump load. The load power factor is 0.6 lagging. The ampacity limit of the conductor used is 100 ampere. So conductor ampacity limit is 100 ampere. A capacitor bank is to be set up at the load in to reduce the current to ampacity limit, that is 100 ampere, keeping the load demand intact. The feeder length is 5 km. The feeder line parameters are this one: 0.8 ohm per kilometer. Resistance reactance is 0.6 ohm per kilometer. Assume load in voltage as 11 kV. Determine this active power demand of the load. So we can make figure before setting up the capacitor or before installing the capacitor. What will be the active and reactive power demand? What will the active and reactive power flowing from the feeder before setting up the capacitor? So this is substation. This is the feeder having this resistance and inductance R plus Jx. It is given as 0.8 ohm per kilometer and the length is given as 5 kilometer. So it will become 0.8 into 5 plus J 0.6 into 5 ohm. So it is 4 plus J 3 ohm. So all the power will come from this feeder PL plus JQL, and this we have to find the active power demand of the load. PL plus JQL. So PL, we know that expression of PL is root 3 VL IL cos phi. PL will be, PL is root 3, VL is given as 11 kV load in voltage. So 11 kV, 11 into 10 to the power 3, and IL is given as before compensation 120 ampere, and cos phi is given as zero point 0.6. Load power factor is given as zero point 0.6 lagging. Therefore, this active power demand of the load is 1371.78 kilowatt. Therefore, D is the correct answer. Yeah, for problem 10, you can directly use, we have just solve, we know this, you just know this slide. I think familiar with this slide that Gaungli sir has covered in the last, in that module reactive power conversion with the capacitor banks. That is the last slide. From there, it is directly coming as for lambda is equal to 0, that is informally distributed load. The power loss reduction will be 8 upon 9 per unit for the capacitor placed at 2/3 per unit distance with capacitor size of 2/3. So this is well known 2/3 thumb rule. So from here you can just remember what you can say. So the power loss reduction will be 8 upon 9 per unit. So that will coming as 89%. So this is thumb rule for single capacitor bank placement for uniformly distributed load. That is the more practical case. In spite of lump load, we having this uniformly distributed load. For the lump load, there is no much needed calculation, because for lumped load, what you have to install the capacitor at the end of the feeder only. But for the uniformly distributed load, you have to take care all these things. So here, if we have single capacitor bank, double capacitor bank, then here we have to install and what should be its capacity. Most of the question will be asked from the single capacitor banks. So just take care of this single capacitor bank expression. Now the next problem is that determine the load current in MVA. So how we can find the, sorry, load, not load current, load demand in MVA. Therefore you have to find the apparent power. So we know that apparent power is root 3 times VL IL. So VL is 11 kV, IL is 120 ampere. So you will get 2286.3 kVA. So you will get MVA as 2.286 MVA. So C is the correct answer. Anything you want to discuss till here, we can discuss. Otherwise, we can move forward. Yes, C is the correct answer. Jaswant, Rahul, both of you are correct. Now, determine the capacitor rating. Now, it is little bit lengthy problem. We have to find the, first we have to find the reactive power demand, and then we can find the reactive power supplied by the feeder. Then we can find the reactive power supply feeder to the load, and then we can find the reactive power supplied by the capacitor. So for this, first we can make the diagram. So after setting up the capacitor, after setting up capacitor, so let us take this feeder having this impedance is given as 4 plus J3 ohm. Now the load is connected to this node and having demand of, we have find this demand. So PL is given at 1371.78 kilowatt and QL we found 1829 kVAR, and this capacitor bank installed. So we have to find the capacitor rating. So first we will find this QC and then we'll find the capacitor rating. So PL, active power will be this PL from the that flowing from the feeder, and the reactive power flowing through the feeder we can take it as Q feeder. This will be QL minus QC. So let us let us find this QL that I have already written, but you can find with the this expression root 3 VL IL sine phi. So we have not find this active power, we have find this active power and this apparent power. So QL will coming as root 3 11 kV into IL is 120 ampere, and before compensation power factor is zero point 0.6, therefore sine phi will become zero point 0.8. So QL will become 1829 kVAR. Then how we can find this Q feeder? So Q feeder you can find many ways, but so let us see this way. Here it is given that ambiguity limit of the conductor is given as 100 ampere. So we will use this data. So S feeder we can write apparent power of the feeder is root 3 VL IL, and this IL will become changed to 100 ampere because the maximum limit is 100 ampere. So root 3 11 kV into 100 ampere. So it is coming as 1905.256 kV. So if we know this Q feeder, we know this apparent power of the feeder and we know this PL. So with the help of power triangle, we can find this reactive power supplied by the feeder to the load. So therefore reactive power supplied by the feeder to the load. So Q feeder will be apparent power minus active power square under root. So this S feeder will be 1905.256 kVA minus 1371.78 kilowatt is the active power demand. So it will give you 1322.2 kVAR. Now this reactive power flowing from the feeder we have found. Therefore, the remaining amount of reactive power will coming from the capacitor bank. So the remaining requirement of QL has to be supplied by the capacitor bank. So this is QC. Therefore, QC will be QL minus QL dash QL minus QL Q feeder. QL is 1829 minus 1322.2 kVAR. So this will give you 506.84 kVAR. So that is approximately 507 kVAR. Therefore, correct answer is B. Yes, Sujata, you are correct. Very good. Now, one may, if you don't want to solve this by phasor method, you may solve by this instantaneous method using with the help of current expression. So I I have already solved with this instantaneous expression with the help of current, not by this reactive power or active power. So another method you can write. Here we know this load current is 120 ampere and we know this lagging, it is of lagging nature 0.6. So we can find cos phi and this angle sin phi 0.8, and this feeder current limit is to 100 ampere, and we have to then we can find this capacitor current. So first we have taken the reference of this phase voltage, that 11 divided root 3 0 kV, and then we can write the current with the help of this reference. So IL will become 120 at the angle of minus 53 because it is of lagging nature, and this capacitor is always in quadrature with the voltage capacitor current. So and this is leading in nature, so you can write IC mod at the angle of 90 degree, and let us assume I feeder as 100 at the angle of minus theta. So this we have assumed. Now just apply KCL. I feeder is equal plus IC is equal to IL. You can solve and just equate the real and imaginary parts. So upon equating the real part, you will get the theta, that is 43.945 degree, and upon equating the imaginary part, you will get the current magnitude, that capacitor current magnitude. From here you can find this reactive power being supplied by this capacitor bank. So it is 3 into V phase IC, V phase 11 upon root 3, IC magnitude 26.6 ampere. You will get from here also 507 kVAR. So you can also approach this way. This is not recommended. I think previous one is better, but you may find this one also interesting. So let us see the next problem. In this problem you have to find the power factor of the feeder after capacitor placement. So this is very simple. We have already found PL, and power factor is cos phi. So power factor of the feeder will be active power upon the apparent power of the feeder. So PL will be remains same, 1371.78 kilowatt, and apparent power will be 1905 kVA. So it will give you 0.72 lagging. B is the correct answer. Okay, we have four attendees right now. Sujata, you are correct, and Rahul, you are also correct. So let us see the next problem. Here in this problem, we have to find the voltage drop magnitude. So voltage drop magnitude will be current into line impedance. So voltage drop magnitude will be I into Z. I, that is ampacity limit. Ampacity limit is given as 100 ampere, and Z will be R square plus x square under root. I is 100 ampere, and this is 4 square plus 3 square. It will give 5. So this will come as 500 volt. So C is the correct answer. We have now 4 more questions, then we will close the session. C the correct answer. Yes, Rahul, you are correct. Now moving to the next problem. So in this problem, it is not numerical type. Here it is asking that the capacitor placement in power distribution feeder to appropriate locations and appropriate sizes results in. Options are lower power loss, better voltage profile, capacity release of the feeder, and D option is all of these. So what do you think? You can tell, or you can type your answer.
All of this.
Yes, correct. Very good. D, all of this. So here there are some benefits of capacitor placement for distribution networks. It helps in it release the distribution substation capacity, and it reduce the energy losses. It reduced voltage drop and consequently improved voltage regulation. It released the capacity of feeder and associated apparatus, postponement or elimination of capital expenditure due to system improvements and or expansions, and revenue increase due to voltage improvements. So these are benefits from the capacitor installment in distribution networks. Now the next problem is that the analytical approach shows that the best location in view of power loss reduction for single capacitor bank for a distribution feeder with uniform load density. So what do you know? Which is the best location for the uniform load density? Uniform load density means lambda is equal to I2 upon I1.
Two-third of the length.
Yeah, so which is the correct answer? So IT is equal to
Option
0,
C.
so lambda will become 0. Yes, at the 66% of the feeder length. So option C is the correct answer. We know that optimal single capacitor bank location x1 optimal will be 2/3 into 1 upon 1 minus lambda. For uniformly distributed load, since I2 equal to 0, there is no load at the end of there is no reactive component current at the end of feeder. So lambda will become 0. So if you put this, it will become 2/3 into 100%. So it is 66.6% of 66.66% of feeder length. Now next problem. So the same problem as it is, but here they are asking about the lump concentrated load. So the analytical approach show the best location in view of power loss reduction for single capacitor bank for a distribution feeder with lump concentrated load at the end of feeder is. So what do you think? You can give your answer.
Option D.
Yes,
Option D at the end of the feeder.
yes, correct. So there is no point. This is just you apply your common sense because for lump concentrated load, that means reactive power component of current at the sending point or receiving point at the last point, both are same. Therefore, this lambda will become 1 and this x1 optimal, we know that it is 2/3 of 1 upon 1 minus lambda. So if you put lambda equal to 0, lambda is equal to 1, then it will give you, it will tends to, x1 tends to infinity. So this indicates the end of feeder. Other way also, because all loads are concentrated at the end of feeder, so you have to also install the capacitor bank at that place. This indicates the end of feeder. So D is the correct answer. Now next problem, the analytical approach shows that best size in view of power loss reduction for single capacitor bank for a distribution feeder with distribution load is. So you have to find the C value and the options are 1 per unit, 0.66 per unit, 0.5 per unit, 0.25 per unit.
Option B, 0.66 per unit.
Yes, correct. So it is the thumb rule that capacitance size should be 2/3 and the for the uniformly distributed load that is lambda is equal to 0. So for uniformly distributed load you have to so this is thumb rule that this capacitor size should be 2/3 and it should be installed at the 2/3 length of the feeder. So this is the best size in view of the power loss reduction for single capacitor bank. So the correct answer is B. C is equal to 2/3 per unit or 0.66 per unit. Now next problem. If a capacitor bank used used in distribution network, some capacitors are kept fixed and some switched. Why do we follow this? And the options are only fixed capacitors cause over voltage during light loading condition. Switched capacitor is costly option. C option is frequent capacitor switching causes transients and disturbances. And D option is all of these. So what is your answer?
Option D.
Yes, correct. D is the correct answer. Because all are yes correct statement. We just only install fixed capacitor, then we will see over voltage during light loading condition. So to avoid this, we also have switched capacitor. But anyhow, we have to just take care of both this fixed capacitor and switched capacitor because switched capacitor just we install only switched capacitor that is also costly option. So we have just some part of conversation that includes fixed capacitor and some parts include switched capacitors. And third option is that frequent capacitor switching causes transient and disturbances. Yes, that is also true. So there that's why we have some parts fixed capacitor only. And some problems I have included from the last year session that I've already solved, and I think that I have already discussed. So if you want to go through these problems, you can just revise and and just gets hands on this problem so that you will feel confident while solving the problems on reactive power compensation. So that's all. If you have any doubt, you can ask. Otherwise, we can close our session today. I think only 5-6 persons are very punctual. Just one Dharmender, Sujata, Rahul, and Lekha. Any doubt or anything we can discuss. Otherwise, we can close our session and we will meet at the same time on the next week. Thank you all for attending this session. Bye. Good night. Okay, I think someone has doubt. I have some doubt regarding reliability related problem. Yes, tell. Yes, Dharmender, you can speak. Dharmender, are you here? Yes, you can tell. You can speak also. You can unmute your mic. So reliability indices are very like in that we have to do nothing. We have to just take care of all the expression, and in the reliability models you have to just see how we will see for the series and parallel combination. So I think if you have I don't know what type problem you have, what type of doubt you have. Dharmender, you are typing or okay. So I think you are out of stress. So you can just mail me personally or message me personally. We can discuss. No problem. Okay, no problem. Therefore, we close our session today and we will meet on the next Saturday. Thank you all.